Hi, my name is Maddox Gambetta, and I did my experiment on encoding colors in a quantum computer. Introduction. In camera surveillance systems, the efficient use of feature selection in an image is required. One of the main forms of feature selection is color selection, which utilizes the RGB values of a video or image. Image recognition via color selection on a classic computer is inefficient, however. A quantum computer, which processes data in a different way, allowing it to perform far more efficiently than a classic computer, is way better suited to this task. The goal of my first article was to study the necessary requirements for classical computers to keep up with the increasingly more powerful AIs. What they found is that the amount of computational power used to train the largest AI models had doubled every 3.4 months since 2012. This is a major reason why quantum computing is so important, because it would allow us to keep up with the advancement of AI. The figure on the right represents the increase in the required computational power to run the AI models. The goal of my second article was to build logical qubits for quantum computers that are able to balance control and coupling with coherence. They found that classic computers do not have enough processing power to run quantum problems, but a new computer is getting further developed called a quantum computer. The first one became available to the public to use over the cloud in 2016, and it was created by IBM. The figure on the right represents the physical and logical layers of a quantum information processor, or a qubit, which is the basic unit of computation in a quantum computer. My third article, called Establishing Quantum Randomness, had the goal of establishing the difference between a qubit and a quantum bit via quantum randomness. What they found is that if a coin was flipped on a classical quantum computer once, then on the classical computer, there'd be a 50-50 chance of either side, and on the quantum computer, there'd be a 50-50 chance of either side. If a coin was flipped twice on a classical computer, however, there's a 50-50 chance again of either side in a classical computer, but a 99.3% chance of it being on one side on a quantum computer. What this means is that for some reason, qubits can undo randomness, therefore making them different from their classical counterpart bits. Figure on the right, it represents the single Hadamard gate circuit, otherwise known as the superposition circuit. This is what I use to run the program of flipping the coin. My problem was I want to know if color encoding can be done more efficiently on a quantum computer than on a classical computer. I believe that if color encoding is used in a quantum circuit, then a quantum computer can encode far more efficiently than a classical computer. The goal of my research was to encode into a quantum computer and test if color can be encoded more efficiently. In my experiment, the role of Universe Mentor was for me, the student, to create quantum circuits for color selection, create images for use in testing, test the computer's color selecting capabilities, and create new tests for the computers. The role of my mentor was to provide me with access to scholarly journals and articles, assist with the construction of quantum circuit and programming, provide me with the resources to learn about the topic and gain expertise, and provide professional opinions on the features and algorithms utilized. The first step of my experiment was quantum computing over the cloud. This is a step where I set up the requirements and tools I would need for my experiment. The first thing that is required is a computer or a laptop with the QuizKit software developer kit installed. Access to IBM Quantum Services. The IBM Quantum Services provide real quantum computers that can be programmed over the cloud. And the system that is utilized on the IBM Quantum Services is a system called Bogata. Bogata is a 5-qubit system. On the right, you can see a representation of the 5 qubits in IBM Cube Bogata. The next step entails selecting the best qubits. Qubits 3 and 4 were used as they have the highest T1, T2 values. The higher T1 and T values mean more efficient and accurate experiments, as you can see on the right. The second step of my experiment was representing a picture via pixels. First, I broke an image down into 2 pixels, and each pixel was represented by 1 qubit. The images are broken down into pixels labeled qubits 0 and qubit 1. On the right, you can see this 2-pixel image with a qubit for each pixel. I then selected colors and the combinations. The colors chosen for testing the encoding were the following 7 colors. These 7 colors are the colors of the rainbow, otherwise known as Roy G. Biv, or red, orange, yellow, green, blue, indigo, and violet. I selected these colors because of how common they are and how they fit in with just how we perceive the world. I then created 3 combinations of these colors. They entailed yellow purple, blue red, and orange indigo. I then collected the theta values. In order to change these colors into a number or an function to RGB to point was developed. This function calculates a different number for each color. The third step of my experiment was creating the quantum circuit for encoding color. In this step, a quantum circuit for encoding colors was created. This is shown in figure 8. Each qubit represents one of the 2 pixels, and the value theta in the phase gate for both pixels is set by a function RGB underscore under 2 point. I then ran the experiment. I ran the experiment 10,000 times to ensure accurate statistics, and I then measured the phase using another function to convert the output of the quantum circuit into an estimated phase. This comes in important later because it allows us to test if encoding colors in a quantum computer is really more efficient. I then, for the fourth step, I did quantum circuit for true colors. In this step, I want to represent a true color, and to show that a quantum computer can encode and measure all colors, I create a true color image. This image was converted into 20 pixels, and each one of these pixels was 96 points apart. The values for theta were obtained in the results section and will be discussed later on. On the right, you can see that this is the circuit utilized for encoding these colors. And that if you go from left to right on the circuit and left to right on the true color image, you can see that all the theta values line up. Results. My first table is the true color table, which shows that the encoded and measured theta values are incredibly close to each other with a 0.27% error, meaning that it is incredibly accurate to use a quantum computer to encode true color, and that you can also use true color and the encoded values to estimate a color. For example, 1.94 would mean the color is violet, and 1.94 cannot mean any other color. And another example would be negative 1.74 would mean the color is green, and that no other color could be green. The next table was my color circuit for encoding a singular color and comparing the different sides of the image. The percent error for my results on this one was 0.33%, which again shows that encoding on a quantum computer is highly accurate, and that you can also use the quantum computer to tell the difference between the colors of 2 sides of an image if you were to use the table from before in reference. For example, negative 3.02, if you were to go onto the quantum circuit for encoding all true colors, if you look between 18 and 19, you could estimate that it was probably red. The next table is encoding the double colors in the quantum circuit. Here you can see that both sides have a different theta value, meaning that both sides are a different color. And yet again, if you were to go over here and look at 0.527, you could see that it is most likely in the blue range, while negative 3.02 is most likely, yet again, in the red range. And again, as you can see, there was nearly a 0.30% error on this data, showing yet again that color encoding on a quantum computer is highly efficient. RGB values have a unique theta value, and all values can be mapped out on a color wheel. The different numbers are referred to as theta or an angle, and these can be encoded into a single qubit using quantum phase with a phase gate. This here is the color wheel we developed, and as you can see, each theta value has a unique location on the color graph. When comparing a qubit to a bit, only one color can be encoded per bit, and true color needs 24 bits. A single qubit, however, can encode a true color, meaning that a single qubit is at the minimum 24 times more powerful than a bit. When comparing colors via breaking the picture down into pixels, each pixel being a qubit, one can tell if an image is blue/red or orange/indigo or yellow/violet. And then colors on a color wheel. In the final experiment, all colors were encoded into a quantum computer by breaking up an image of true color into 20 pixels. From the measured values in the first experiment, one is able to estimate the color, and it agreed with the image that was used for encoding. Yet again, this graph is the representation of the theta values and their respective colors on the graph. For future research, I hope to implement machine learning in a quantum circuit, use existing color encoding data to train the quantum computer to use machine learning to recognize the patterns in the data, repeat the test to verify the pros and limitations of machine learning while encoded on a quantum computer, and the potential implementation of further data sets in order to test the capabilities of machine learning when paired with a quantum computer. This here is representation of the potential circuit for color encoding with machine learning. In conclusion, my problem was, can color encoding be done more efficiently on a quantum computer than on a classical computer? And I hoped to encode color in a quantum computer and test if color can be encoded more efficiently. I believe that if color encoding is used in a quantum circuit, then quantum computer can encode more efficiently than a classical computer, and I found that color encode can be encoded in a quantum computer with far more efficiency than a classical computer. This is my presentation on color encoding. Thank you for watching. My name is Max Gambetta.